Alright, in this section we're going to be looking further at calculating probability, and we're going to be looking at the classical probability formula. So to get us started with that, we're going to look at sample data set number 22 on page 145 in your book. We've got the data set here in the table below, and we're going to be solving for the probability of selecting someone from this particular set that has a result that is a false positive. Now, before we move into solving the problem, let's take a few minutes and look at the 4 different outcomes you always get from any measurement tool so that we can better understand the complexity of the situation when we move forward. So, any particular measurement tool is going to be composed of these 4 possible outcomes. So, you're going to have a false positive and false negatives. The false positive is when we say the particular event occurred in the case the person is using drugs, when in fact it did not occur, the person is not a drug user. A false negative is when we say the person is not using drugs when in fact they were using drugs. So here we're saying that the event did not occur, and in fact we are incorrect, the event had occurred. Now, any measurement's also going to produce true positives and true negatives. So here we see a true positive is when we say a particular event occurred, and indeed it did occur. Or the true negative is when we say something that did not occur, and in fact it did not occur. Now, when looking at this, your probably first reaction is, well, we just need to have a more accurate measurement, and then we will not have these problems of false positives and false negatives. Although that sounds like a really good idea, intuitively, when we look at how measurements are conducted, we're going to see that, in fact, it is impossible to ever fully remove these 2 components from any measurement outcome. So, a word about measurements here. Looking at this figure here on the right, we're going to use this to kind of go through and talk about the 3 components that make up any measurement. So, the first of these is the true score. Now, a true score is the actual degree or amount of item we are interested in measuring. So you can see option A over here on the right, the primary amount of the measurement visually is made up of the true score. So this is a really good measurement right here. It's got high reliability and high validity. Now, if we look at the second one below at option B, we're going to see that a great deal of the measurement is actually made up of random error. Random error is just chance. So these are all the different random things that could go on while conducting a particular experiment for each individual. So you can think of random error as being kind of dirty windows that have not been cleaned for an incredibly long time, and you're trying to look out the windows and see something outside, and you have a very hard time seeing through it because the windows are so clouded and dirty and smudged. That smudge and dirtiness of the windows, you can think of it as being the random error that's getting in the way. It's hindering your ability to actually see what you really want to see, which in this case, for a measurement, would be the true score. Now, option C here has a high degree of what we call systematic error in it. Systematic error is the product of a particular measurement or tool or environment that we're using for the study. So examples of systematic error that we've looked at previously in this class would be ordering of particular questions or leading questions. Now, since each individual completing a survey has that same leading question, it is what we call systematic. It's built into the system of the particular research design. So it is a systematic error, but it is still a problem as it is still clouding the issue of the true score we want to get at. So, ideally speaking, what we want to do is produce a measurement tool that's very much like option A here at the top. So we have high reliability, high validity, the majority of the space is made up of the true score. But keep in mind, even in this preferred situation, we still have a certain degree of systematic error that is the product of an individual, for example, filling out a paper and pencil survey, and this random error that happens in any particular activity that we're doing. So, anytime you have a measurement and you're working with the outcomes of the results, you need to keep in mind that those outcome results will all have a certain amount of false positives and false negatives in them. This is really important when we look at probability and we look at making expectations. We need to be accurate in our statements and not overstate how accurate we are because we're ignoring the fact that any measurement has systematic error or random error in it. That is a serious flaw. You need to not do that. So keep it in mind as we move forward. Anytime you're working with outcomes from any particular result study, you're going to have a certain amount of true score, a certain amount of systematic score, and a certain amount of random error. And that systematic error and that random error is going to produce a certain amount of false positives and false negatives. All right, so now that we've kind of shifted gears over there and talked about the reality of doing measurements and what any measurement is composed of, let's shift back over here and start looking at doing some statistical analysis with these particular results. So for this particular problem, we're going to use the classical approach to probability. Now, this is a different formula than the one we used last time. So let's take a look at what's different between the two problems. And that way you'll be able to identify when you're working with the problems yourself which particular formula you need to be using. So this first problem over here, when we're looking at the probability of selecting someone who's got a result that's a false positive, in this problem there's an equal likely chance of each of the simple events occurring. So selection of a single subject constitutes a simple event in this particular problem. And as each person has an equal chance of being selected, all 1,000 simple events are equally likely. Notice, in this particular problem, we are not asking the probability of the drug test outcome overall. We are asking about the probability of selecting someone with a particular characteristic from the specific given set. So this is a very important attention to language and selecting the proper formula for solving a problem. Now, I always hear from several students that they don't like word problems and when can they solve problems without word problems. And I have bad news for you about that because you're going to be using word problems. So the classes that you'll be going on to after taking this class, whether you're going to risk management, whether you're doing a marketing research, whether you're going into chemistry or any of the other sciences where you're doing hypothesis testing, all of those are word problems. So they are not strictly working with numbers. And one of the important things you need to know, indeed a critical first step, is knowing what type of problem you have and what approach you need to take to it. So this is what you need to be bringing as the expert when you move into your classes and when you move into a job where you're going to be using this. So once again, any software program is going to be able to run a particular formula for you. What it can't do is figure out which formula needs to be used. That's where you're needed. So looking at this, we can see that we're paying attention to the fact that we're selecting someone from this particular group, and that allows us to use the classical probability approach. Okay, so we're using this formula here. And when we're looking at this other problem, the Y-sort technique, notice in this problem we're using a sample to make an estimate about a particular population. So we're using a sample of 291 births, and we're trying to use that to make an estimate about a larger population issues such as the effectiveness of the Y-sort technique. Thus, we cannot be certain that all simple events have an equal chance of occurring. We can't be sure of that. Because we can't be sure of that, we have to err on the side of caution that in fact they won't. This means we have to use the relative frequency approximation formula that we have here. So just to sum this up, when we're looking at something where each simple event has an equal chance of occurring, we use the classical approach to probability. And if we have a simple event that does not have equal chances of occurring, then we use the relative frequency approximation. Now, although these look very similar, do keep in mind they are different in important, subtle ways that we'll be looking at later on. So let's go back to solving this particular problem here. We're looking at the false positives. You can see I've written up here on the whiteboard on the right. In this particular problem, A stands for selecting someone whose test is a false positive. I've sketched out the formula there, so we have the number of ways A can occur. And we're going to divide that by the number of different simple events. And here we can see that false positive is what we're interested in, so that is a total of 90, and that goes in our numerator. And here we can see our denominator is the all possible simple events, so adding up all of those, 44 plus 6 plus 90 about 860 equals 1,000. And going through and doing the calculations, we get the answer that the probability of selecting someone from this particular set of subjects whose result is a false positive is 0.090. All right, this concludes this section on looking at the calculating probability. Next up, we've got going through and looking at the steps of solving a probability problem, where we're going to go through from the very beginning and work all the way through to the end.